Thank you for the opportunity and everyone else for coming. It feels weird being the one at the board now. So my talk today is about the project I've been working on. So it's a work in progress. The first part is already on the archive. So it's canonical forms. I really think of them as like existence and uniqueness theorem. So the existence part has been written up, and currently I'm working on proving uniqueness. But to get started, I want to sort of mention a dictionary due to a current workman. That's going to sort of be the underlying motivation for the talk. And so this dictionary says that there are some relationships or analogous statements between statements about arithmetic groups. So let's say just GL and Z, or mapping class groups, or compact surfaces, or other automorphism groups of free groups. And when I say free, you should always assume I mean finitely generated free. So these groups, just from their definitions, they're very different. But you can prove their statement, they're sort of surprisingly a shocking amount of statements that end up being corresponding like analogous statements in each case. So the one that I want to focus on today is you have Jordan canonical forms in GL and Z by thinking of them as sitting inside GL and C. You have Nielsen-Thurston canonical decomposition of mapping classes, so I'll describe that as well. And at the moment, there's no analogous like complete statement for canonical forms of automorphism groups or free groups. So let's start with GL and Z, which will be really quick. I'm not going to belabor the point here. So you have Jordan canonical form. And I'm also going to just focus on specific cases of it, or pieces of it. So an element of GL and Z is going to be an automorphism of the free abelian group of rank n. I'm just going to call it A. And I want to let this live inside n copies of C, n products of C. And the Jordan canonical form says that you can now actually get a direct sum decomposition of our vector space, where some of these are associated with eigenvalues that are greater, whose magnitude is greater than 1. Some of them are associated to eigenvalues magnitude less than 1. Since it's an automorphism, it's going to be positive. And then some of them in the middle will have eigenvalues equal to 1. So these are going to be like the expanding spaces. These are the contracting spaces. And then these are, I don't know, like unipotent spaces. And this decomposition is nice because it's actually preserved by our automorphism. So the automorphism of Zn extends to an automorphism of Cn, and it's going to preserve this decomposition. So over here, we have we can restrict the automorphism to get automorphisms of these subspaces. And the subspaces VI are generalized eigen spaces. And what you should really think of as meaning that AI, so the restriction of the automorphism to these eigenspaces, has specific forms. The details are not too important here, and I want to focus on today's focus is the ones where the eigenvalue is greater than 1. So the expanding dynamics of this automorphism are the ones I'm going to talk about.
Probably you should write a little bigger on the next board.
Okay. I do have a tendency to write small, so let me know. Okay, so, and I'm not going to, knowing the details of this is not really important to my actual talk, but I wanted to motivate the reasons why I'm going to focus on expanding things only. And now with surfaces, for the mapping class group, here we'll have the Nielsen-Thurston decomposition. And so what is the mapping class group to begin with? I'm going to focus, for simplicity's sake, assume
bigger.
Assume the Euler characteristic is negative. So you can, these are compact, I already put compact there. So it's compact surfaces with negative Euler characteristic. That allows you to use hyperbolic geometry in some of the proofs, even though I'm not going to discuss the proofs. And the mapping class group itself is defined as a group of homeomorphisms from the surface to itself up to isotopy. This can also be written as the connected components of the homeomorphism group. The definition I'm giving is a bit non-standard, just FYI. Typically, mapping class group will focus on orientation preserving homeomorphisms. And when you have boundary, because I'm talking about compact surfaces, typically you sort of want it to be the identity on the boundary. But I want to move on to the outer automorphism groups of free groups. So I'll just take the more general, this more general definition of a mapping class group. So now what does the Jordan Canonical Form, what is the analogous statement for the Jordan Canonical Form with surfaces? I'll just draw a picture of it. So you have a surface. I'm going to draw a close surface here of genus 5. And so this surface has a homeomorphism F, but I really want to study F up to isotopy. So most of the things I'm going to be discussing will not necessarily be true about F, but will be true about something isotopic to F. So if you give me a mapping class of this surface, then the Nielsen-Thurston decomposition says I have some, again, sort of like a direct sum splitting of my surface. So I have a bunch of invariant subsurfaces. Call them, I don't know, S1, S2, S3, S4. And these are going to be invariant under my mapping class. And the restriction of the mapping class to each one of this is a mapping class of a smaller complexity. And then each one has a specific form again. So we want to say that Fi has two forms. It either looks like a twist or a multi-twist. So there are a bunch of sort of like distinguished, there's a distinguished multi-curve. So a bunch of simple curves on your surface that are not parallel and they don't intersect, they're all pairwise disjoint. And on a regular neighborhood of this curves, so I'm just going to draw one of them, the homeomorphism, the mapping class does this. If you sort of take a curve, it twists it to where I've done a twist 2 times here, but it could be n times or however many times you need. So you have a Dane twist about each of these distinguished curves. I don't know what else to say. So that's going to be called a multi-twist. And it's somewhat like the analogous thing of when you have eigenvalue 1 here. Almost unipotent if you pass to a power. And then, yeah, so maybe you want to pass to a power just to be safe, because maybe the homeomorphism actually permutes this invariant curves. So pass to a power, then that power looks like this. And then the most interesting for us.
Wait, does the component have to look like that? Like
what?
It's one.
No.
No. Okay.
The component can look like any of this.
Okay, I see.
Yeah. It just has to be a compact surface with a negative Euler characteristic. Yeah. Okay. And then I'm drawing this component like this, but you should really think of this as one of these SIs here. The second case is the most interesting one, which is going to see the exponential dynamics. So on this surface, you're going to have foliations. So you sort of want to say that locally, in most places, it looks like you have a foliation by lines where I don't know, it's like you've put a grid on your surface. But because I specifically chose this to have negative Euler characteristic, the Poincare-Hopf index theorem says you can't have such a foliation on the surface without singularities. So index theory tells you must have singularities. And so one of the singularities could look, I'm drawing a 3-pronged singularity, but you can have 3 or more in general. Will look something like this. So now you have, you have these foliations that share the same singularities, and all the other leaves are sort of transverse to one another. So yeah, you have two independent directions. And now the homeomorphism looks like a Nassov map with respect to these foliations. So what does that mean? Locally, you're sort of going to map this foliation. How should I do this? And then the transverse foliation in red maps to something that looks like. So can you appreciate what I'm trying to sort of show here, which is I didn't mention this before because when I just discussed foliation, I just mentioned it as a topological thing. But these foliations actually have locally, you can sort of, in each chart of your surface, locally you can put a distance. You can, you can define a distance between the leaves of this foliation. And you want, for one, like the yellow pair, you want the distance to stretch between the leaves. And then for the red foliation, you want the distance associated to it. So that's the transverse measure. If you're looking at, that's what it's usually called, transverse measured foliations. In the red one, the distances between the leaves are shrunk, and by the same factor. So white stretch by lambda in one of these directions, and 1 over lambda in the other.
Sorry, can you clarify what happens near the boundary? Is it like diagonal, I mean, transverse to both of these foliations?
So in the boundary, my foliations, I want my foliations, one of the restrictions I should mention is there should be singularities on the boundary. And so on the boundary, you should sort of think of it as looking like this. So this is the one part where the leaves are not transverse, because the boundary is going to sort of be part of the foliations of both of them, under my definition of this.
In that case, the boundary is a leaf.
Yeah, the boundary is a leaf. So here on the boundary, it sort of looks like, I don't know, some like north-south dynamics where things are moving towards the yellow lines and then away from the red leaves, or the other way around. And again, in the boundary though, you might have just one. It doesn't have to be 3 or more. You can have 1 or 2, or so you can have 1 or more separatrices coming off of it.
It's consistent with I think in Minju Lee's talk, there was what's that Nassov? But the linear Nassov, this is mimicked on the linear Nassov map, where you have, say, something in SL2Z, with the eigenvalue bigger than 1, there's a contracting direction, expanding direction.
Yeah.
This is just much more.
So it's like a branched
version
of your typical Nassov. Oh, and I didn't put the name here, but this will now be the pseudo-Nassov. I guess a bit of historical thing here. Nielsen sort of studied mapping classes around the 40s, I think, or maybe 30s. And he had quite a lot of this data where he understood that if you given a mapping class, there is a way to sort of decompose. And I believe his description was already somewhat like canonical in this sense. So he didn't quite have a full description of what these other pieces should look like. So he understood that there was some unique potent looking like pieces and irreducible pieces, but this description of these pieces is due to Thurston, of the pseudo-nasals, it's due to Thurston.
So I can keep track of this one. We should think of it as both the lambda bigger than 1 and lambda less than 1.
Oh, so yeah, here I'm really just going to forget one of the foliations and just think about the one that are stretching. Yeah, but I want to thank you for bringing this up before I raised it. I want to highlight one thing about one difference. With the surface case, like the expanding things only had essentially eigendirections, like these were honest eigendirections. Whereas here in general, you sort of expect, you have eigenspaces, but this generalized eigenspaces are like hierarchy of things. So you can have non-trivial Jordan blocks in the Jordan canonical forms. But in this case, it's like your blocks are always, like your expanding blocks are always semi-simple. And that's not the case in GLMZ in general. So it's the structure of surface homeomorphisms sort of rules out this generality, but it turns out it's not that simple for other automorphisms of free groups. So that piece of having some interactions with eigenspaces and needing to think about generalized eigenspaces is important for free group automorphisms, even though you never have to worry about it with pseudo-nasals.
So under this analogy, in the mapping class case, you only have 2 Jordan blocks. I guess 2 semi-simple VIs.
No, but you have a pair for each of the circles.
Oh, right. Oh, I see.
This is sort of a rank 1 phenomenon for the mapping class group.
I guess.
Is there any reason for S4, you chose the genus?
No.
2 things?
It's just, I guess I didn't want you to think it's always going to be genus 1 things in the pieces, but yeah. So for example, there's no reason why you need to even have subsurfaces. So like S1 could be the whole surface. And so the whole surface could be a pseudo-nasal homeomorphism. Your decomposition could be just the whole surface with no.
But in general, it could act as pseudo and also from like one piece, but not.
Yeah, and not on others. Yeah. I'll give a picture of that in a moment with while discussing our automorphisms. So now the question here is, what about out F? And I want to, in line with the restriction of having negative Euler characteristic, I want to restrict myself to the case where the rank is at least 2. For completeness sake, this is the automorphism group modulo the inner automorphisms.
You want the rank to be the most powerful.
Finite. So it's less than.
Oh, fine. Oh, yeah. Sorry. Yes.
We're not getting into that.
Yeah, finite. I need it to be finite and at least.
So just the statement of the Nielsen-Thurston is that those are the only two types, right?
Yeah.
Like no shrinking.
What?
Like there's no option for shrinking at something. Either it's
Up to isotopy, right? Yeah, so up to isotopy, it will look like this or like that. And again, up to like powers. Because this is not necessarily true unless you pass to a power.
And that's common in the linear case too. You say quasi-unipotent.
Yeah.
Powers unipotent.
And oh yeah, so the canonical thing about this is that these subsurfaces are unique up to isotopy as well. So if you were to give a different description that looks like this, then you should be able to sort of pair up the decompositions together and show that the homeomorphisms were essentially the same as well. So it's canonical, so you don't have to make any choices to give that description. All right, so now let's look at out F. Is there a canonical decomposition of an automorphism or a free group? As far as I know, there is none. But we have specific examples where if your automorphism is special enough, you will have such a decomposition. And one of this is a cheap one, is like the mapping classes. If the surface has boundary, then its fundamental group is a free group, and the mapping class group embeds inside the automorphism group. So for that image or that embedding, you essentially have a canonical form, but I want to have one that doesn't rely on some surface theory. So let's translate this statement about foliations into something that could possibly apply to things that don't come from surfaces. So let's understand geometric automorphism. Automorphisms. S is going to be a compact surface. I want it to have with boundary and negative Euler characteristic. So that tells me that the fundamental group is going to be a free group of rank at least 2. And I want to identify this with the deck transformations of the universal cover. Of the universal cover. And this is mainly my way of sort of hiding base point issues under the rug. And our automorphism and by thinking about things in terms of the universal cover, I end up not thinking about really the automorphism group, but rather the automorphisms. But that's not a big, it's not a big deal. This is going to be induced by a lift F tilde of a homeomorphism F from S to S. So I start with a compact surface. It has a mapping class F. I lift to the universal cover, and that's going to induce an automorphism of the deck transformation that satisfies this equivariance relation for all points in the universal cover.
You're using F for both the free group and the automorphism.
That's capital F.
But we're not expecting to see Frobenius. Then we'll really get confused.
I hope I remember TSG from now on.
Make a little F. How about a little F?
That was supposed to be a little. So for all points P in the universal cover and all elements in the free group, G tilde of X times P tilde is phi of X times G tilde of P tilde. And I'll sort of like say this means that G tilde is phi equivariant. Take this as a definition of being phi equivariant. So the thing to take away from this is whenever you lift to the universal cover, you have multiple lifts you can choose from. And the multiple lifts are going to give you different automorphisms phi that differ only by an inner automorphism. And so all the lifts are going to parameterize all the entries in the outer automorphism group, in the outer automorphism class of phi. Okay, so now let's see what the canonical decomposition is. I'm going to draw another big surface here. So we have some surface. How much genus do I want to put in this? Let's say. And its invariant surfaces look somewhat. This is just an example. And in this piece, I wanted to be, I was using yellow for the previous one. I want there to be a pseudo-Nassau here. So some foliation here, it might have some similarities. And we have another foliation here. On the surface that are preserved, and they have transverse meshes that are stretched by lambda. And then over here, I want it to be like the uniported thing that I just erased, but I don't really care about the important things for today. So I'm only going to focus on the expanding dynamics. So pseudo-Nassau with, so this is S1 with lambda 1 greater than 1. And this is a pseudo-Nassau with associated lambda 3 greater than. We have an S2 here, which is unipotent, quasi-unipotent. Okay, so now let's lift to the universal cover and see what happens. So in the universal cover, it's really hopeless to draw, but I'll try. I think I'll just do those two. So this is our S2 tilde. It's just one copy of it. There are going to be lots of other like disjoint copies in the universal cover. And then here we'll also have sort of like we have this foliation inside how did I go? S3 tilde here. We have S1 tilde here, and S3 tilde here maybe, and then S1 tilde here. So the thing I want to sort of describe is that the foliations here are going to lift to foliations that are still invariant under the deck transformations. And the transverse measure, remember earlier, the transverse measure was sort of defined locally. Like locally, I could put a distance between the leaves. I can lift that to the universal cover and put like local distance between the leaves. But the nice thing about the universal cover is now I actually have no obstruction to sort of extending that to like a global distance between any two leaves you give me. So any two leaves here, if they're within the same, any two leaves inside S1 tilde, connected component of S1 tilde are going to have a distance, all right? And then I want to now say that things that are separated by S2 tilde are distance 0 apart. So like, sort of think about this whole thing. I'm removing this chalk. So
Zero, it's like different, in different.
just think of them as one piece, like, because I'm going to define an equivalence relation.
So that's a uniform.
Yeah, so everything in the unipotent thing and like the boundary, I'm just going to consider as one point in my equivalence relation. Okay, so I'm going to look at the space of leaves. With the added restriction that I'm really thinking about this whole component as part of the leaves. The closure of that as part of the leaves. And now at the quotient, I'm going to get a matrix space. I think I called it TD. So the points in this space are the leaves of this. And the distance between them is given by the distance that comes from this transverse measure. Now this metric space is actually really nice. It's very, it looks like a tree, and it's not a simplicial tree, but it is sort of like a metric tree. It was termed as an R tree.
I missed this. How do you measure distances between two leaves in different things?
So if they're in different components, you just sort of add. If I have a leaf here, I can measure the distance to this boundary.
Oh, the boundary is a leaf. Which
And the boundary is a leaf, and the boundary is part of the leaves here, right?
I see. Okay, okay.
Like you should think about your
Enter
foliation.
the boundary and then you exit the boundary at the same distance, zero distance.
Zero distance, yeah. Now this is an R. This is an R tree, which means that it's geodesic. So any 2 points can be connected by an arc that's isometric to the an interval of the real line. And any geodesic triangle, so if you pick 3 points, you can join them by geodesics. The union of any 2 sides of your triangle contains the 3rd side. So triangles look like tripods. The union of 2 sides, P, Q, R, is going to contain the 3rd side. Triangles look like tripods. So it's a geodesic metric space where triangles look like tripods. If you've seen delta hyperbolic spaces, these are 0 hyperbolic spaces where delta constant is 0. And
so in general, you want to consider all the foliations universe to be at 0 distance from each other.
Like the whole surface is going to be given distance 0. So just
Or for every universe piece.
Yeah. Yeah. Oh, so now if I had like 2 of them, that's going to sort of like be 2 disjoint points, like distinct points. Because they're going to be separated by an exponential thing in between. Okay, I don't need this anymore. So here's what the statement now says. Nielsen-Thurston decomposition. And I guess this is the exponential expanding form. So it's not quite Nielsen-Thurston decomposition because I'm completely forgetting everything that's happening in the unimportant pieces. But it still sort of sees all the expanding information here, is that there exists a tree, PD, an R tree, class, I have an action of my free group on this tree by isometries. That just comes from the fact that I lifted the measure. And so in the universal cover, the measure was sort of preserved by the deck transformation. So I end up getting the deck transformations induce an action by isometries on this tree.
Let's see, the tree is associated with a automorphism. We first have the automorphism.
Oh, yeah.
So we fixed one automorphism.
Yeah.
Okay.
I'm going to, it's one of the points here.
Good.
So there are other properties about this action. It's minimal. I don't know if it's obvious to see this here, but what that means is there's no proper invariant subtree, non-empty invariant subtree. So it's the smallest invariant subtree, non-empty subtree in this. And you have trivial arc stabilizers. And what that means is if you have a non-trivial element fixing a point, then it fixes a unique point. You never fix an arc, an undegenerate arc in your tree. And again, that's not sort of, you sort of want to know something about these foliations to really see where that comes from. It's because with the pseudo-Nassau foliations are going to be irrational. So they don't have any closed leaves inside other than the boundary. They don't have any closed leaves. And then point 2, so now I'm going to remember my mapping class. There is, let me first describe it before I write it down. We had a homeomorphism F or G, sorry. we had a homeomorphism G, and then I lifted it to G tilde. So that's going to be a homeomorphism of this that preserves the foliations. Because G preserves foliations, G tilde is going to preserve these foliations. And the distances were being multiplied by lambda, right? Well, by like lambda 3 here and lambda 1 here. So when I collapse, I'm going to get a homeomorphism of my tree. And this tree has some subtrees, like corresponding to, I don't know, like T3 and T1. And on those subtrees, it's a homothet. It's multiplying T3 by lambda 3, and it's multiplying T1 by lambda 1.
You said that F is acting by isometries?
Yeah.
Oh, F is
F is the
Yeah, the F is the fundamental group. G is the homeomorphism.
Now, the T should really be a T sub phi or T sub T.
Yeah. So
Just so we don't get confused, the construction, we first fixed this transformation. We made the tree, then you have the free group acting on this.
So I have a homeomorphism that is phi equivariant because G tilde was phi equivariant. That's why I sort of went into the pain of defining the phi equivariant. And I don't really know what the proper way to call this. It's a dilation. You sort of want to say it's a homothet, but it's not really a homothet because you have different expanding factors on different trees. So I've gone with calling it a dilation. And the point here is that T is covered by translates by orbits of subtrees T1, T3 in this case, but in general, you're just going to have one for each pseudo-Nassau piece. So, in my example, it's T1 and T3. And H restricted to Ti is lambda I homothet.
I'm sorry, I'm a bit confused. So this means that, I mean, in the first point, it means that a deck transformation cannot take like something which was expanding to something which is unipotent.
No, I mean, the deck transformation is going to preserve the subsurfaces, right? So, so it's going to send S3 to a translate of S3.
I see. Okay. Yes. No, okay. I know. Of course, you're right. Yeah.
So yeah, it preserves the dynamics, and so I'm sort of like saying that T. I don't know. I talked about direct sums earlier, so you can sort of think about T as a direct sum of T1 and T3. And so in T3, you have an expanding thing. So this is like an eigen direction, right? I have eigen trees, T1 and T3. And then the third point that's somewhat interesting is the point, like which elements of my free group fix a point and which ones don't. X is going to fix a point, fixes a point if and only if you think about it as represented by a loop on my surface, then that loop can be homotoped into my unipotent piece, S2. So X is but I don't want to talk about surfaces. So I'm sort of giving a description that says nothing about surfaces. So X is linearly growing.
Not exponential.
It's not exponential. Or yeah, you can say X doesn't fix a point if and only if X is exponentially growing. So in general, if you don't have a surface, what does this mean? You can pick your favorite basis of F, and then you look at how fast the length of the conjugacy class of X grows under iteration of your automorphism. So this is really a statement about the conjugacy class rather than the element X.
Can you say what does it mean for H to be phi equivariant?
It's this here, but now with H instead of G tilde. So you should think about, like, what does it mean for H to be equivariant in general? You have an action of your free group on the domain and the codomain. And you sort of, when you're saying equivariant, you're saying that action is, in a sense, commutes with H. But in this case, in the codomain, you're changing the action. It's not acting the usual way. You're first applying the automorphism and then acting. So it's like equivariance where you've changed you've twisted the action in the image by applying this automorphism first. And the prototypical example of such a thing is lifts of things to the universal cover are usually not going to have the X appear in both sides. You're going to have to twist.
So if I were a group theorist, which I'm not, but maybe they are, and I wanted to understand the use of this in terms of like canonical form, I first start off with the element that I'm trying to understand, phi. I make this construction, and then you're going to be able to tell me guys which commute with phi or something like that, right? Or the centralizer, something of that nature.
Yes, so the usefulness of having a canonical description or canonical form is it allows you to understand which element centralize phi. And so
and if we actually took a free group on 5 generators and wrote down some Nielsen transformation, you could make the construction here like you would compute eigenvalues of a matrix. It's effective, right? So suppose we actually, can you implement it to compute the lambdas?
The lambdas, yes, but the tree, I don't know how to describe how you want to describe such a tree. It's like this tree has an orbit of a point is dense.
Yeah, it's minimal.
It's minimal, but
I mean, how do we?
It's like you should think of like simplicial trees are like rational numbers, and these trees are like algebraic irrational numbers. So I don't know how you will describe such a tree to a computer. Foliations, on the other hand, have like charts. You can describe them in terms of train tracks, but I don't think anyone's given such a description for R trees in general. So computability, I'm not entirely sure how useful that is.
I mean, but what you're really doing is, as you said earlier, that if I have an element in the mapping in the outer automorphism of the free group, and I apply it repeatedly, I'm looking at how the growth rate of conjugacy classes, for example. You're saying there's a structure to that. I would imagine that somehow finitizes so that you actually kind of apply it. Anyway, it's
yeah, like qualitative properties about this tree or quantitative properties about this tree can be computed, but I don't know if the tree itself.
Okay, all right.
Like, I think you might be able to describe things like how many branch points it has and how many, but I'm not sure that's enough to sort of like reconstruct the whole tree.
These are probably pretty special R trees.
The ones that come from surfaces?
Yeah, I mean.
Yeah, like this, because I'm starting with surfaces, these R trees can be described, but in general, I don't think your R trees are going to be nice enough to be able to do that. I don't think I need this anymore. All right, so why did I go through all this work of translating this? It's because this statement now says nothing about surfaces.
Yeah.
And so that's sort of like the goal of my project is if you now give me an automorphism and you don't tell me that it comes from a surface, can I is there a tree like this? Oh, I should say, I guess I'll just say it, but it's unique, right? It's canonical. Everything that I've done so far, okay, uniqueness is a bit too strong, but it's canonical. In this case, because I didn't make any choices. I just started with a canonical decomposition from like surfaces, and then I lifted to the universal cover, and then I collapsed. Everything was sort of like predetermined. So this tree is canonical. And with a little bit more work, you can show that it's unique in the sense that any tree that satisfies these three properties is essentially going to be this tree, possibly with like T1 rescaled and T3 rescaled by something. Like if I multiply the metric on T1 by 5 and the metric on T3 by half, it will still satisfy all these properties. But that's the only.
An R tree, what is the formal definition of an R tree?
The formal definition of an R tree, a geodesic metric space whose triangles are tripods.
Okay.
Is that equivalent to being zero hyperbolic?
Or a zero hyperbolic space.
Can I ask a question?
Yes.
Please. So this uniqueness thing you said, you don't even need to describe the action. Like you just say there's an action of the free group by isometries, and there's a commuting thing, and here and it's you. I'm just trying to.
So I could start with another tree like Y.
Yeah.
Is an R tree with an action of F by isometries, and it has H prime, a homeomorphism that's a dilation, and elliptic points are exactly the things that are linearly growing. And then I'm saying that tree Y is actually covered by orbits of two trees, Y1, Y2. And Y1 is equivalently sort of like homothetic to T1, and Y3 is equivalently homothetic to T3. And I can sort of extend that to a homeomorphism of the whole tree. So the only thing I can do to really change this tree and still have all these three properties is to rescale T1 and T3. And that's a very strong statement. In this case, I could say it's true because all these trees come from surfaces. And if a tree comes from surfaces, we know that the foliations are unique. And so that's like Thurston's theorem, that those foliations are not just like nice foliations, but they're unique foliations. So
Can we have empty decompositions?
Yeah, the Nielsen-Thurston decomposition is unique.
So which corresponding to your future world populate this.
Yeah. Okay, so now let me state the current, or all of this I was sort of like aware of. None of this is new. So Nielsen-Thurston's work, Thurston's work was around 70s, 80s.
Or can you say what linearly growing means?
Okay, so formally, you fix linearly growing, or polynomially growing. Would mean that X is polynomially growing means that if you look at the length of the conjugacy class with respect to some basis, but it doesn't matter which basis. So what is the length of a conjugacy of an element? The conjugacy length of an element is you write it in your basis, and then you look at the shortest cyclically reduced word in that conjugacy class. And now you're asking, how does this grow? And I really don't want to get into like the technicalities of asymptotics, but you sort of wanted to say that this is bounded by a polynomial. Polynomial in N. The polynomial might depend on the element X. Yeah, so when I say linearly, it could in fact also be sort of like, in this case, it could be constantly growing if it's periodic, for example. Sort of like, all those is going to be polynomially growing. And exponentially, exponentially growing since I said I was interested in the exponential dynamics, is you sort of expect this to look like lambda to the n. The conjugacy classes are growing asymptotically to this exponential function. And it's a theorem of Besviner-Handel that for an automorphism phi, every element is either going to be polynomial or exponential. So there's sort of like no super polynomial sub-exponential growth or anything like that. So you have this dichotomy. And this tree sort of recognizes this dichotomy because the loxodromic things are going to be the exponential things and the elliptic things are going to be the polynomial growing things. Okay, so original motivation. Given an automorphism, I want to say that there exists a tree 2D satisfying 1 and 2. Rather than just repeating myself, it's those two conditions there. And then 3, I want it to be X is elliptic or fixes a point if and only if, rather than have linearly growing. So with surface homeomorphism, you ever see linear growth, but in general, you can see like any order, given an automorphism in general that doesn't come from surfaces, you can see quadratic or cubic growth. So I want to say X is polynomially growing. So it's essentially this statement with linearly replaced with polynomially growing. That's what I wanted to prove. And it actually proved quite difficult. And then I started starting to think it's impossible. And uniqueness, right? You sort of want to prove that it's uniqueness. But even the existent question, just the existence of a tree satisfying these three properties, I'm starting to think no such tree exists in general, because I'm asking for too much. I want to have a metric on an R tree, and then I want to collapse everything except everything that's polynomially growing, and only the polynomially growing things. And when I was proving this, it just seems like the proof wants you to collapse more than just the polynomially growing things. And if you only want to collapse the polynomially growing things, then you end up having to lose the metric. So I can in my preprint I have an existence theorem of some sort of like topological tree, and it has an action of the free group that almost looks like an isometry, but I don't have a metric. But it looks like an isometry, and it's a lot harder to sort of describe what it means to be a dilation in that case, but sort of once the things are expanding, and an element fixes a point if and only if it's polynomially growing. That's not very satisfying, so let's keep metrics. We want to keep metrics here. So I end up having to compromise on the third condition. So I want to collapse the polynomially growing things, and I don't know what to, there is no name for this as far as I know. So X is exponentially nested, which is best described by example. But this sort of highlights the thing with like Jordan blocks not being trivial, like having generalized eigenspaces rather than just eigenspaces, right? So yeah, I'm going to describe it. I'm going to give you an example. But it's like I said earlier, like with surfaces, it's sort of special because your exponential things were semi-simple, but in general, you don't sort of expect them to be semi-simple. So that's what the exponentially nested is trying to capture. But here's a definition by example. I have an automorphism phi. Let's say F equals the free group on A, B, C, D. The first case where such a thing becomes a problem is rank 4 or higher. So it's a high rank phenomenon. So, my automorphism is going to send A to A or AB, B to BA, B. So, trust me on this, that this is an automorphism. And then C is going to go to, C is going to go to C, 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 C is C, looks like CD. So it's it looks like what I'm doing here, but I'm just going to insert D. So this automorphism is like, oh, what it's doing on A and B and C and D look exactly the same right now. And all I'm doing is adding an A inside. And if you start iterating this, you will notice that not only is this thing growing exponentially, but you're going to see exponentially longer segments of A's and B's in between. So I'll have C goes to CAD, and then A goes to AB, and then D goes to C, D, C. This piece here went to this piece here. And if I kept on iterating it, I'll start seeing one segment here that sort of looks like A being iterated here. And this grows exponentially. So over here, I'm going to see an exponential part. Yeah. So this is exponentially nested. It has nothing to do with the growth rates. So I could have chosen any automorphism here and any automorphism here, but as long as I'm seeing longer and longer segments of the A's and B's here, I'm calling that exponentially nested. So here's another example to really sort of, I'm going to define by example, what does the complement look like? Let's call it psi. Exactly the same as before on AB. CD looks exactly the same too, almost, not exactly the same. D, C, D. But rather than put A, I'm going to put the commutator of A and B. So A, B is A, B, A inverse, B inverse. And put that here. So now, again, trust me, this is an automorphism. But now, if I actually chose my automorphism on AB properly, this here is a fixed element. So the commutator gets sent to the commutator. And so if I iterate this, I'll never see any growing segments of A's and B's. C, A, B, D, E, so that went to this, and you can sort of like see that if I start iterating it, it's not going to expand. So this here is not exponentially nested. Now I'm out of time. But with that statement, if I try to describe this tree here, then this tree is going to be forced to collapse A's and B's here. But trying to describe this tree for this example here, I'm not forced to collapse A's and B's because they're not sort of like intrinsically linked together. Even though I'm seeing A's and B's inside C and D, I'm seeing a periodic version of them. So that's somewhat fine.
So what's the upshot? where you're at in terms of your construction of.
Yeah, so the most difficult part was sort of recognizing like what's the thing that I need to actually modify the third point, and currently it's sort of like formalizing this idea. I can sort of like explain, give an example and a non-example, but writing it down formally is sort of like what I'm.
So that at this point in your preprint, you have an action, you have this element of the automorphism of the free group. You can construct. Are you making it a tree or not? You're saying you have to compromise. So what do we do?
Yeah, so the preprint that's out, it wasn't a metric. I lost the metric.
Okay.
And then I got an action on a tree-like thing. But the action looks like isometries, and it satisfies essentially points 1, 2, and 3, where the elliptic things were the polynomially growing things. But without a metric, you really have no, like it's completely topological. So proving uniqueness is really hard because I don't have any tools to study it without a metric.
Are there numbers lambda that are associated with it then? Are there these exponents?
Yeah.
Are they unique at least?
Yes, but those were already known to be unique. So the numbers, like the exponential growth rates, all these things are sort of already known. It's the tree that's really good. But most of the quantitative questions you can ask about the tree without asking for the tree is already known. So I had this topological tree, action satisfying all the things that I wanted, but proving uniqueness was hard because I didn't have a metric. So there are barely any tools to work with. And now with this extra condition, I can get a metric and I can prove uniqueness.
You said this wasn't a problem in rank 3. So this was only a problem in rank.
Yeah, it's not a problem in rank 3 because I sort of needed 2 pieces of exponential things happening. So in rank 3, I can't have C sort of like having exponential dynamics because it's sort of like rank 1 mod AP.
So is the uniqueness true for rank 3?
Yeah. It's not written out, but because I didn't want to do something that was just special for F3, but yes. In F3, you don't have to worry about this and the tree existence.
F2, of course, is just.
And in F2, things are known because all of them are geometric. They come from surface or homeomorphisms on a punctured torus.
Let's geared towards us two who only look at F2, at least. I only look at F2, and I think Will has also liked F2.
Okay, so in all of this also phi is assumed to be geometric. So it's induced by some left homeomorphism.
No, the whole point is not.
Oh, it's not.
No, so now with the motivation, it's not. I sort of want to get the same statements that I know about geometric ones for all of them. But geometric ones, it's known to be true. And that was like the picture that I gave earlier. But now I'm trying to say it and prove it without assuming anything about surfaces.
You get phi as a composition of 2 geometric ones with different geometrizations.
In that case, you're sort of now land here. Like the geometric stuff doesn't, once you compose them and they're in different like surfaces, then.
Right, that's what maybe phi is. Can you see phi as a composition is in some insightful way?
These trees are not functorial. So if you know the tree for phi 1 and the tree for phi 2, I don't think
That's what I was asking. The construction depends on the,
it doesn't really help you to see what the tree for phi1 composed with phi2 looks like. So yeah, knowing them for geometric things doesn't really help you to understand the compositions of them, if the composition is not geometric. I think I'll stop there.
Yeah, maybe let's finish and thank Jean-Pierre.